Thank you very much. Thanks for allowing me to speak here. I mean, it's been really nice to be here with so many nice people to talk to and get all the ideas. And thanks for coming, of course. I mean, I know the weather is very nice, and you'd probably prefer now to sit somewhere outside, have an ice cream, but you actually came here to listen to me. So, yeah. So this is all joined with Gijs Huids. So unfortunately, he's not around anymore this week, but he definitely did help me out last week, so that I don't tell you any lies today. Okay, so we start with this result of. Sorry.
You are actually allowed to
Great. All right. So, well, the other great thing about giving a talk in front of this audience is that I don't have to explain to you what's a K and local spectrum. So I start directly with the result of Greeley's and Sadowski, and also Hovey-Sadowski. Which says the following things: a theorem that let E be K and local with a G action, where G is finite. So we have a K and local spectrum with a finite group action. Then you can form a Tate construction, and turns out that it's K and localization vanishing. So that's this kind of a duality result. Now, how is this duality? Well, equivalently, you can phrase this as you can take homotopy orbits and you can look at the norm map and G going to the homotopy fixed points, and then of course the tail is the cofiber of that. And why is this some sort of duality result? Because you basically are saying that homology and cohomology are K and locally equivalent. So K and locally, we know that this norm map is an equivalence. So that's equivalent to this statement. Okay, so and let's see what does this give us in examples. So I start with example 0, not example 1, but example 0, because it happens in the height 0. So it's an example 0. So if E is rational, well, then what we know basically, I mean, then we know an obvious fact in group cohomology that the Tate construction in this case is just 0, because well, then we know that the norm map is an isomorphism from 0 to homology to 0 to cohomology. Okay, so now another example I can give you is example 1, which is then height 1. So in this case, so this was actually example when n is 0. Okay, so now I can take example when n is equal to 1, and in this case I will take a specific K and local spectrum. So K1 local spectrum. Well, prime P is fixed, of course, P fixed. K1 local spectrum, Kp, which is the periodic K theorem. Is there anywhere here a watch I can control the time? Or? There, I can see the screen. Yeah, that's great. Yeah. So periodic K theory spectrum Kp. So what happens in this case? Well, we can ask ourselves, what does this theorem tell us in this case? Well, it does tell us that K1 localization of Kptg is trivial. In this case, G is acting trivially, and most of this talk, eventually G is going to act trivially on this K and local spectra. So that we know, but we know even more. We actually can, well, this as a consequence has that in fact this is rational. This is rational. That's what we know. This is rational. Okay, and we know even more if you take if you take homotopy groups of this, negative homotopy groups of this state construction, well, it's the same as, yeah, I mean, that basically is a result of many people. Well, maybe it goes back to Attia Siegel. Maybe in this form, it's stated somewhere in Greeley's-May, and maybe some other references here, but it turns out that this is isomorphic to the following thing. So it's a sum over a bunch of copies of QPs, where this is a number RP, and I'll tell you what that number is when star is equal to 0. And it is 0 when star is equal to 1. And that's all you need to worry about, because complex K theory, periodic K theory, and big K means periodic K theory, is of course 2 periodic, and you don't have to worry about other degrees. So RP here is the number of conjugacy classes. I mean, it's basically character theory. Conjugacy classes of order of elements of order p to the d. P to the d for some d. And I think these are the d greater or equal than 1. So I'm taking non-trivial elements of order p, because if I would take a trivial element, then I would also include something else, and this is exactly tape that doesn't see the trivial element. Okay, so that's the story in the height 1. So what's the story in higher heights? Okay, well, let me introduce this notation just to make my life a bit easier. I'll denote the homotopy groups of this state construction as like state cohomology, like het state BG. So that's just going to be a notation for state cohomology. So in particular here I could have written like KP hat, but let me not do that. Okay, so now height 1 case, height 2 case, or higher height. So example n greater or equal than 2. So it's not an example n where n is greater or equal than 2. It's like we can take any k in local spectrum. Well, let's take En, which is Morava E theory, or Lubin-Tate theory, so Morava E theory. At height n, I mean, you can take some variations of this this thing. I think like many of them would work. Like I think the list is given in the HKR paper, but so you can take one of these Morava E theories. This is K in local. In local, in some models, it's K in local E infinity ring spectrum, but I don't need that. One thing I can tell you about this E theory, I will just denote it by E to make my life easier. Well, I can tell you maybe what's homotopy groups. The one maybe I will be considering. Well, one of them is like you can take width vectors over fp to the n, and then you attach the power series generators like these up to n minus 1. This all lives in degree the zeros, and then here you have this bot class which lives in degree 2. So in particular, when n is equal to 1, this is exactly the p-adic K theory. That's why I like to generalize it like this and not in some other way. So just that it aligns with that example. So now the consequence of this theorem is that if G is finite, then the Kn localization of the Tate vanishes, where again, like the action is trivial in this case. Okay, and of course that tells you now that the information you need to worry about are, of course, the various lower localizations of the state construction. So it's this, maybe K1 localization, etc. Kn minus 1 localization. So these are, of course, the things to try to figure out. And I will not tell you anything about these things today, because this is this transchromatic character theory, and I will not be touching that. But I can tell you some things now, of course, the classically what was done in this case, and then I'll try to generalize that in the other cases. So and here, this is where the Hopkins, Kuhn, and Ravenel character theory comes in. Ravenel character theory. So one of the ways to interpret this character theory is to actually try to understand this thing. So what is that thing? I mean, in fact, it does understand this whole thing, but then like there is equivalent ways to rephrase this character theory either by understanding this or rationalization of that. Okay, so I'll try to focus on the date side today. Okay, so in any case, so what we need now is when you do character theory and representation theory, you need to attach roots of unity to things. Otherwise, it's difficult to do character theory. So you need to do something similar in this case in order to be able to actually do some kind of character theory. So for that, you need to define some big ring, which basically is a cousin of or generalization of the ring that was attaching roots of unity to the yeah, like when you take rationals and you attach all the roots of unity. So the way the Hopkins, Kuhn, and Ravenel do this in their paper is they take E theory of P Z mod P to the R to the N. Okay, so this R is going to go to now to infinity, and N is going to be, of course, fixed. N is exactly this height. And then you can take a goal limit of this. You can take goal limit of this along when R goes to infinity. Well, this is just along the obvious projection maps, the backwards maps, and then you take goal limit. And then you localize this. This is a ring. This is a ring. If you take a direct system of rings, it's going to be a ring. And then you can localize this on some set S, where I can tell you actually what this set S is. S is the set of all possible first Chern classes for this kind of homomorphisms. Of course, these kind of homomorphisms give you a vector bundle, and then you can take its Chern class. So you can take this kind of thing that gives you something on classifying spaces, and then you can take its Chern class, and then you can localize with respect to this set, this ring. And turns out that this is a good enough ring, a graded ring, which I want to denote by C star. Well, that's what you call C star. And now maybe I'll give you an example. Yeah. Yes, thank you. Yes, thank you very much. Yeah. Yes. To the end and the non-trivial. Yeah, exactly. Non-trivial characters into S1. Yeah. Thank you. Yeah. Yeah, I should maybe say like injective or something here. Yeah. No? I should. Oh, no. Sorry. Yeah. No. If I would be there doing this, then yes. But yeah, these are just like homomorphisms from here to there, like with the image in Z to the something. Yeah. Yeah, thanks. Okay, so you need to take all of these non-trivial Chern classes. Yeah. Right. And also, what happens when N is 1, maybe we should mention this. Well, this kind of recovers in this story. Well, in fact, there is a bit more here to recover that story, but like let's talk about this later. In this case, C star ends up being the following thing. It's you take QP, you attach to it zeta P infinity, and then you have the bot class. So that's basically what it is in N is equal to 1, this thing. But in general, it's a bit difficult to describe. But what additively we know is that it's always is an algebra over the rationalization of this coefficient ring. So it's the rationalization of that. There's always algebra over this, so in particular it's a Q algebra. So it's some big rational ring which sort of is good enough now to get some kind of character result. So one thing maybe I can also like maybe formally make this writing like this. So we know that there is a map, of course, from E to EQ, and then into this C. So I will not write now stars because like I can view this as this is an algebra with that. So this is an algebra with this ring spectrum, and this is an algebra with this commutative ring spectrum if you want, and then I will draw a diagram in spectra then, which of course gives you a diagram in long exact sequence as well. But let me write it like in the following way so that you see the picture. So you can form this kind of sequence. Homotopy fixed points, and then you can form here the date. So you can draw this kind of norm sequence. I mean, of course, here is the norm tensor over E with the C, because then this norm map is an E module map, and you can just like everything happens in E modules, so you can tensor it with C. But then there is, of course, the corresponding norm sequence for C, which is here again the norm for C, and here you have the Tate with respect to this C, and here of course you have the fact that this is modulo over that allows you to sort of write down this base change map. And now an obvious observation, of course, is here it's not homotopy orbits, it's homotopy orbits here, and it's the fixed points here. Sorry for that. So then obvious thing is that this commutes with homotopy orbits, so this is going to be equivalent. Well, this is not necessarily an equivalence, but this is here an equivalence, because that is 0, because we were rational. Okay, so as a consequence, and I'll write the consequence here, and then I can start writing the stuff in the new board. As a consequence, you get that if you base change the cohomology to this big character ring, okay, so what you get is a sum of two things. So it's a homotopy fixed points of this plus the date of that, right? So it's the date of. So that's a consequence. That's what you get. And the level of spectra, and then you can take homotopy groups. Why is that? Because, well, that shows that this, because these two are equivalences, this shows that this is a splitting, right? That's a splitting. And so it really splits as whatever that is, which is equivalent to that sum of this and this. Okay, so in order to understand, like, and what Hopkins, Kuhn, and Ravenel do is to actually write down a formula for this thing. But I mean, I told you now what this thing is in terms of date, so basically it's the same as writing down a formula for date. Okay, so that's what we get. Maybe I can like go a bit up here and just delete this board. Right. So now, what is the actual formula that HKR gave in their paper? So I can also write that. Can also write that down. Actual theorem is that in fact this is the theorem of Hopkins, Kuhn, and Ravenel. Theorem HKR is that if you take a finite group and then you take its E theory, and okay, you cannot directly yet say what's a rationalization. Later they also explain what's a rationalization, but in this formula I still of course will work with this big character ring. Then this is always isomorphic to, let me write it in the following way, in a bit of awkward way. You will not like, but later that will be helpful. So it's like homology of BG with this coefficient C star. And don't bug me on gradings because I will get all of them wrong. It's like the double grading here going on and you need to figure it out. Plus the sum over conjugacy classes G1 and so on, Gn, and tuples living in the following set, which I want to, well, let me call it like this. So let me write it like this, G1 and so on, Gn, and here I'll write this GNP minus, how should I write this? GNP minus the trivial tuple modulo G. And what are these things? And here a copy of this C star. Now, of course, this thing here is C star itself, because it's a finite group, and we're talking here about rational cohomology of finite groups. That's just like a copy of the coefficient. And the reason why I wrote it like this is because I had this thing here, and the homotopy groups of that is just rational, it's just the cohomology. But the point I want to make is that whatever that is, that's exactly this date. Now, what is this GNP? I mean, this GNP is Gn, P. This is a set of the form G1 and so on Gn inside the G to the N, where Gi, Gj commutes. I mean, these things commute with each other for different indices, and each of them have p power order. So Gi has p power order. Okay, so that's all of these things together. Now you remove here the trivial tuple because the trivial tuple went in here, and of course I have that copy. I could have written this as index on all tuples, including the trivial, but then I would not have this separate thing. But I want to have this separate thing to make a point that this is exactly this part. And of course, G is acting on this thing by component-wise conjugation, right? So G acts by conjugation. Conjugation in each coordinate. And so basically a consequence of the HKER theorem is that, that we know what's the date construction. So we know exactly if you take date construction of this BG, base change to this C star, or the same as homotopy groups of the date, and then you base change to C star. So it's like date interpretation of HKER theorem. That's exactly isomorphic to this part. So I mean, I can write this out again, like it's conjugacy classes of these G1 and Gn's. I will not repeat where it lives, and it's in this here. Or another way to write this is this kind of functions, class functions on this G and P minus the trivial tuple mod G, and then you take functions into the C star. Okay, so that's what happens if you base change to a very big rational ring, which you kind of pretend that you understand. Then as a consequence, what they get is actually they calculate the full rationalization of this thing. You can also write down here a formula. Now you need to start acting with the GLN of ZP and things like that, but I don't want to go into that because I didn't generalize that part. So I should not talk about it. Okay. Okay, so that's the story in the finite group case. So you are trying to use this duality result. So in order to like, okay, you know that Kn locally it vanishes, but what happens below for the state, and at least rationally you have some good answers thanks to HKR. Well, in between you have some good answers as well thanks to Nat Stapleton. This is this transchromatic stuff, but I mean, again, I didn't generalize that stuff either, so I will not go into that direction. Okay, so that's for finite groups. So now what I want to do is to generalize this for infinite groups. So to generalize this for some infinite groups. And I mean, there are some various motivations for this to do, and maybe some of them I can even explain. I can even maybe explain today, but like there's many reasons why I got interested in this thing at the end. So probably I won't be able to mention all of them. So generalize this for some infinite groups. Now, of course, the story itself has been generalized in many different directions by several people, and one of the first observations here is that there is a generalization of the norm map due to John Klein. So it's Klein's norm map. There is a Klein's norm map which is ridiculously general, that goes from, that has this kind of form. It's like E tensor DG. Homotopy G orbits goes to homotopy fixed points, and then there is this state. So there is this twisted version of Klein's norm map, which works, I think, in some ridiculous generality for any topological group, maybe even something that you can actually write down this map. And the way you define this DG, it is some kind of adjoint representation sphere, at least in this setting. So what you do is you take suspension spectrum of G, also known as spherical group ring. And this has two actions. It has actions of G cross G, because, well, it acts on the left, it acts on the right. And now you can take I think the left action and the fixed points with respect to that. So you take homotopy fixed points. And then the other action still stays. So it's actually still a G module. So in fact, I could have written maybe here HG in here or the other way around, but let me not go into right and left modules now. Okay, so that's what John Klein did. Now, in fact, John Klein proved for some special cases, was investigating when this norm map is an equivalence, and I think John Rogness was also investigating in some special cases when this norm map is an equivalence. I mean, I think you were calling them stably dualizable groups.
Yeah, Tillman Bauer generalized plans for
P-compact groups, yeah. Yeah, so I think in your case, it's like when the Kn localization of this thing, in the Kn local category, this is like dualizable or something like that, yeah. So what I'm going to do today is to go in the orthogonal direction a bit, what Klein did and what John Rogness did. Okay, so yeah, so for what kind of groups am I investigating this map today? Well, if you have seen me before, then you probably will guess that these are the groups which have finite E under bar G. Yeah. And then it turns out that this is kind of the reason why this case is cool is that because this dualizing complex actually can be described in very explicit way. And that gives you then the key for actually studying the duality. Okay, so what you can do is, well, you can consider, so in this talk, G is a discrete group, discrete group with finite E under bar G. And what is this E under bar G? So E under bar G is a G space which has the following properties. It's a GC-doubly complex. Well, I don't need to explain in this audience what's a GC-doubly complex, I think. GC-doubly complex, and what you can also do is you can take fixed points here, and these fixed points behave in a specific way. So it's an empty set when this is finite. Sorry, it's infinite. Empty set when this is infinite, and it is contractible when this is finite. So in other words, this is a classifying space for the family of finite subgroups, because I think people here know what's a classifying space for families of finite. And I mean, this thing is like very natural thing that shows up a lot in geometric group theory, like things like, I don't know, outer space, diagonal space, all the spines inside there. All of these things are actually examples of E under bar G's. Like all these nice spaces people act on in geometric group theory are these E under bar G's. But I want the finite one. So what is finite? Finite is equivalent. Finite is an equivalent way of saying that the quotient is compact. Some people in group theory also call it co-compact E under bar G. It's built out of finitely many equivariant cells, like the usual thing you would do. And I want to study now what this norm map does in this case. Okay, so that's what yeah. Oh, compact. Sorry. Yeah. Thank you. Compact. Thank you. Yeah. Of course, I skipped it. Yeah. Thanks. So question is, what can we say? About K localization of ETG, and in general about ETG. And I mean, I have to immediately say that like a related question in some ridiculous generality with some pi finite spaces and things like that has been already studied. Like, when is the state construction of something vanishing when something is a finite co-limit of certain things for which it already vanishes? Of course, not in this example case, but like it's related to the work of, I think it's Knossen, Carmeli, Knossen, Ramsey, and Janowski. So these guys are having some general machinery, how you can tackle questions like, when does a date vanish in some general situations? And it turns out that I think maybe like at least the vanishing result, which I will say, which I believe the way we prove it is a bit simpler than maybe what these guys do, but definitely they have much more general machinery where you can, like, if you ever want to prove some date vanishes, then you should check out certainly their paper as well, so to get a general idea what you could do. Okay. Yeah. Yeah, it is. It fits. I mean, this is an example of so-called twisted ambidexterity, which I will be talking about now in terms of, I think Bastian Knossen introduced that terminology in his paper, maybe, or someone else, but he definitely wrote a big paper about that. Yeah. So this one of the results I will say is in that direction exactly. Yeah. Yeah. So, but in order to prove this, like in order to study these things, I need to say more about, well, how exactly does this Klein's dualizing complex look in this case? Because in general, this is not not an easy thing to study. I mean, like, this is basically group cohomology in ZG coefficients, roughly speaking, and that's a non-trivial thing in group theory. That's the so-called dualizing module, which in some cases is not even computed. So what's the way to at least theoretically tackle this thing? And this is where this thing, which I worked with many people, comes in. So this is the proper G spectra help you with that. Well, obviously they do, because you assume that G has finitely in the bar G. So in this setting, you should suspect that some kind of genuine G spectra kind of thing would be useful to study some equivariant objects for these groups. So what are these proper G spectra? So, I mean, this is something, I mean, I did the model category version of this with several people, the Greise, Hausmann, Luke, myself, and Stefan Schwede. So we constructed a model category of these things, but the right way to sort of, I want to think about them these days, after all this theory has been developed, and the model I will be using in this talk is actually due to Linskens. You see here, or you didn't show up at the end, huh? Linsken, he already knows all of these things, so it doesn't have to show up. Linskens, Nardin, and Paul. So what these guys did is they actually told us what this proper G spectra really is. And so here is what this thing is. So you can consider the following category. You can consider the orbit category, or I'll denote it by O fin G. So this is the finite orbit category. Finite orbit category. So what does this orbit category do for you? Okay, so what are the objects here? Objects are G mod H, where H is finite. Okay, G is an infinite group a priori, but yeah, objects are like these cosets for finite subgroups. And now you can form a diagram. You can form now a diagram, which is just doing the following thing. So you form a diagram of infinity categories. So you're gonna form a functor from this. Well, morphisms are just G maps, okay? Like your usual maps in an orbit category, which I think everybody in this audience has seen. So, and now you form a functor of in G up into cat infinity by sending G mod H to SPH, where this is genuine H spectra. So SPH is the model for any kind of infinity categorical model of genuine H spectra you like. And here, if you have a projection map, so this is like a restriction, which means that this is a subgroup of that, if I'm not wrong. Yes, this is a subgroup of that, meaning that you have backwards a map in spectra. So you have here restriction from K to H, okay? So this restriction goes there. I'll denote this also like that. And of course, you have some of these conjugations here as well. These are like honest maps of these things. And they, of course, also give you these kind of automorphisms here. And there is a way to make this into a functor on this orbit category, maps into cat infinity. And now what these guys showed is that Linskens, Nardin, and Paul showed that, so if SPG now denotes the category of proper G spectra, so infinity category of proper G spectra, proper G spectra. So for people who like model categories, what is this category? I mean here, so a map is an equivalence, if and only if the restriction of this map, well, I could also take fixed points if I want to, it doesn't really matter. So if all the restrictions are equivalences in the genuine H spectra in SPH, for all H, any H finite. So in other words, for every fixed point for finite subgroup, if you are an equivalence, then that's an equivalence in this category, okay? Now, what do these guys prove? So what they proved is that, maybe I can like, go here. So what they prove is that, like, if you take inverse limit of this functor, you get this category. So that's sort of a crucial result that you can use to then describe Klein's dualizing compound. in terms of these limits. Okay, so what they show is that there's a theorem well, theorem / definition now, because like you can now, of course, like just remember this, what they showed. So LNP is that this category, what I'm talking about here, is just the inverse limit over this orbit category of in G of this SPHs, or informally, because I will probably be using an easy notation, is limit over restrictions of these SPHs. So you take all possible restrictions. Well, I'm ignoring conjugations, of course. You need to always remember conjugations as well. But informally, it's just a limit along restrictions of these things, and that gives you back this category. Okay. So that's what they prove. And now this is cool because, well, here is one problem this category has. This category, of course, involves something like Gmod H inside here. So it has these kind of gadgets inside. I mean, these are the compact generators. These are compact generators. But as you probably know, in group cohomology, like the trivial G module is often not dualizable unless you have some finite cohomological dimension or something like that. And sorry, it's dualizable. It's not compact, for example. Or vice versa. If you take like this kind of coset where H is finite, this is in fact not necessarily dualizable. So these are compact generators, but not dualizable. So this is one of those examples when this is not like this very popular rigidly compactly generated TT category or something like that. So these things are definitely not dualizable. So typical dualizables in here, typical dualizables are Gmod gammas where gamma is finite index. It's finite index. Of course, when I write these, I mean suspension spectra of these with plus. And I believe I upset John Greeley, I think, in one of the times I was talking in Venice, and then you didn't like the fact that I was not putting plus here. So let me do this now. So that right. So now, if you have this kind of situation, though, what you can do is, well, so now, of course, the problem is these things are not dualizable. So if you do, like, there is no Wertheimer isomorphism or something like this in this for these kind of things. That's one of the keywords for experts. In particular, the usual functional dual. So the functions from some x to s is not a duality. On compact objects, on compacts. Because if you take the functional dual of that, that's going to be some dual of like this G mod H into S. It's going to be some infinite thing. It's not even going to be compact anymore. So it's going to be something funny. Yeah. So problem is we want some other interesting duality functor on this category. So some other duality. H is a finite subgroup, yeah. So in this case, gamma is finite index. Sorry, yeah. Thank you. But I will not really be talking about these guys much. I will be mostly focusing now on these things where H is finite. So my problem is that I have compact generators which are not dualizable. So in particular, the functional dual is not well behaved. So I need to come up with some alternative notion of duality, which then allows me to actually play some games and maybe describe this dualizing complex. Okay, and so the way you do this, you use the result of Linskes, Nardin, and Paul. So what this shows is there is this trick with infinity categories that if you have a limit along the right adjoints, and you do, because this is a limit along the restrictions, and we know all of them are right adjoints, then in fact you can write, that follows from Linskes, Nardin, Paul, that you can also write this thing as a co-limit of the same categories, but now not along the restrictions, but along the inductions. But now this co-limit is in pro L. So you have to form this in the pro L, okay? And now there is this trick with compactly generated categories that such a formula immediately tells you what are the compact objects inside here. So this is the notation for compact objects, compacts. And this compacts is the co-limit over the compacts in here. But now this is an honest co-limit. You don't have to talk about pro L. That's the cool thing about this this trick. Well, obviously I learned this from Gijs. Yeah, yeah. And so now what you can do is like you can define a duality functor on this thing. So of course you have the usual Spanier-Whited duality functor on finite spectra. So this is the usual equivariant Spanier-Whited duality, or functional duality if you want. And the funny thing is that this does commute with induction functors. So it does commute with the usual induction from H to K for finite groups. So for H and K finite, well, I need to write here some ops, I guess. Let's write here ops, op. Okay, so, and this diagram commutes because H and K are finite, and you are using Wertmuller isomorphism. Wertmuller tells you that. So actually this diagram commutes, okay? And now what you can do is you can pass through the co-limit. So pass to co-limit, and you're going to get this bold-face D duality. Like I want to denote it with some different word to distinguish it with from the finite case, from this compact objects in here to compact objects in here. Okay, so and this is a unique op here, of course. So and how is this thing determined? This is a unique exact functor. Unique exact functor with the property unique exact functor which is compatible with inductions from finite subgroups, and Spanier-Whited duality for finite subgroups. So basically what I just defined for you, that it was a co-limit of these things for finite subgroups. Okay, that's good. So how does that bring me back to my date stuff?
Could you just say again how that result is related to the limit over here?
Yeah. I mean, like what I just did is I take this diagram, and this is a diagram again over the orbit category. I mean, I wrote here int, but I mean, I'm kind of doing it over the orbit category. And I have this diagram, and these commute, meaning that there is a functor from orbit category again to cat infinity, if you want, where I just take these as values, and these inductions are the induced maps.
So that's all with compact objects.
Yeah.
It's not with compact objects.
Yeah. Oh, okay. So I mean, what I did here, this is in pro L. So in pro L, this co-limit is a bit difficult thing to compute. But if you pass to compact objects, then it's an honest co-limit.
Okay.
Yeah. And I can define now this D on this category. Then later I can expand it in here as well. Well, this is co-limit in cat infinity, like honest co-limit in the infinity category of infinity categories. This one is co-limit in pro L, presentable with left adjoints.
And can you deduce that statement from the statement
you deduce this from there, and you deduce this from there.
Okay.
So that's the logic, yeah. Okay. Yeah. Great. So that's what it is. So meaning that there is this kind of unique functor because I passed to the co-limits there. Okay. So now what does this functor do for you? I mean, that's the point. So I do construct this functor, which I claim is a duality on finite G spectra, which I didn't have before. And it's a form of Grothendieck-Verdier duality, in fact, with a dualizing object, which shows up in constructible sheaves and things like that. So there is an instance of this in algebraic geometry as well. Apparently, there is this result by Pardon, who actually shows something similar for Orbi spectra or something like this, where he also kind of notices that you don't have a nice duality for compact objects with the functions, and then you come up with this kind of funny construction. His paper is very hard to read. I think you can redo his paper using this kind of technology. He applies this for some orbifolds and things like that. Okay, so yeah, so one thing this functor does for you, if you take a dual of G mod H plus, or a suspension spectrum of G mod H plus, you can see that this is again G mod H, this equivalent to that. which does match with the picture in the finite case, because in the finite case, of course, the dual of the G mod H is G mod H by bipolar isomorphism. Okay?
It's for H finite or for
This is again H finite. So always H is finite. Yeah, this is, I should always mention that. Yeah, definitely. Yeah. So yeah, so that's one observation you make. The other observation you can make is that if you take a dual of the sphere spectrum,
Now, G is also finite.
no, G is now infinite. I mean, I'm talking here since the previous board, G with like everywhere here, G is infinite discrete,
From the sphere, as an H.
infinite with finite end of our G, right? So far, actually, didn't really need to finite the end of our G. Yeah, I do need to finite the end of our G because this is a finite co-limit. I think there I need to finite the end of our G. So let me, for safety reasons, assume this always. Now, so what's the sphere spectrum? Is sphere spectrum even compact? I mean, in this category. Of course, if you do group cohomology, the trivial CG module sometimes is not having a finite resolution. But under these assumptions, actually, it always does. So, meaning that you can, if you have finite end of RG, then of course the suspension spectrum of this finite end of RG, which is the model for sphere spectrum in this world, is also a finite complex, is a finite GCW spectrum, let's say. Of course, this is a bit of a informal name, but you know what I mean. Like it's built out of this G mod H suspension spectra of G mod H's. Okay, so this is a finite GCW complex, and this implies that the sphere spectrum is compact. So it belongs to these compact objects inside this this G spectra. So you can ask yourself, what's the dual of that? Well, turns out that the dual of that is not necessarily S. Well, I mean, it's not surprising because, like, I constructed this functor in some fancy way. It's not just functional dual or something. So why should it be like directly just like sending S to S? I mean, S is not definitely not of this form as well, right? I mean, S is kind of built by some finite attachments of these G mod H's. So a priori, it's not the right thing. Well, there is a way, of course, computing this ds, and that's the theorem what we proved. So the theorem with Gijs, first observation basically we made is that if you take G an infinite group, so let G be infinite discrete, infinite or discrete group. I mean, it can be also finite, but then this result is trivial, of course. Discrete with finite end of Rg. That in fact, this Klein's dualizing complex, dg of Klein, which is the homotopy fixed points of this sphere spectrum, is equivalent to this dual of the sphere in terms of this duality as naive G spectra. Now, of course, when Klein defines this dualizing complex, he just looks at it as a spectrum with a G action. It's a naive thing.
What's a naive G spectrum?
That's just a module over SG, module over the group spherical group ring, if you want to think about it like that. Or, you know, like just a spectrum with a G action in the most naive way. Yeah.
So no equivalence on any fixed points whatsoever.
Yeah, well, this is equivalence as naive G spectra, as underlying spectra. So in some ways, this is a genuine thing, right? And this is sort of a naive thing. And what I'm telling you that this is underlying to a genuine equivariant homotopy type. I got asked last time when I gave a talk this question that this has a G action, and it's a kind of, if you look at this orthogonal spectra kind of thing, then you can also could consider this as a genuine thing. I believe it would be the same as this thing. But the point is not that I am promoting this into a genuine thing. Point is that I'm actually creating something which is very computable as opposed to this. And that's the second part of the theorem. So the second part of the theorem says that in fact there is an explicit way of computing the ds. So if E under bar G, you can write E under bar G as a co-limit of G mod H's. I mean, this is sort of along the restrictions. Let me write it like that. So what does this mean? You can take orbit category, you can consider all these restrictions in between these G mod H's and take a whole co-limit if you want, and that gets you E under bar G. In fact, this can be modeled in a finite way now because I assume that this is a finite unit. So then
this is still over finite h's, right?
this is over finite h's, yeah. So co-limit over O thing if I want, yeah. I can do that, yeah. And now you can, there is a way to compute this dual of S because you know what's a dual of an orbit, and you know this is a unique contravariant exact functor from going from there to there. So I can just apply dual to that finite co-limit. I mean, I know the orbit category is not finite, but I model this co-limit finitely because that thing is finite. So I can just directly apply dual to that. Dual of S is then the inverse limit along the transfer maps of these G mod H's. Now take all possible transfers between these G mod H's and take an inverse limit. And so that's ds. And if you forget the underlying homotopy, equivariant homotopy type and just view it as a naive thing, you recover Klein's dualizing complex. I certainly do pluses here everywhere. I mean, this was with without plus, in fact. But here, this is definitely with the pluses and that thing. Yes, that's true. Okay, so now I can apply this to, okay, so let me just give you one example before I apply this to HKR theory. So one example is, well, I hope I can even apply this thing in studying dualizing modules in geometric group theory, but of course I don't have a concrete result now. I have one example that indicates that maybe this could be interesting. So if you take an amalgamated product of finite groups, L, K, okay? These are all finite groups, H, L, and K finite. Well, then Klein, of course, tells you in his paper what is this dualizing complex. It's either one copy of S minus 1 or it's an infinite wedge of S minus 1s, depending on if you are like VCD1 or VCD, sorry, if you are, if you have a free group of rank 1 inside or free group of higher rank inside, depending on that. But what you can see is that this, I mean, one way of writing down the underbar G in this case is you can take G mod L and you can cross this with a 0 and you can go to G mod H cross G mod K. Well, that's an obvious thing I could do because this is a subgroup of both of them. And now I can attach a cell. So it's a one-dimensional model. And that gives you this, in this case, the E underbar G. That's a push out. So this is a push out, whatever, like that. And now out of this diagram, you can compute what's the dual of S. And the dual of S is the following thing. So you can just read off it from this diagram. So dual of S is from this diagram. You can easily see that. Well, I mean, stably, what this diagram really tells you is that if you take G mod H and you go to G mod L, G mod H plus G mod K, and I should be doing pluses again in suspension spectra as well, but I'll let you not write that. So this is restriction minus the restriction. If you take the co-fiber of that, that's the sphere spectrum in this case. So that's the co-fiber. So now you can just dualize this diagram. So you see the dual of sphere is a fiber of the following map, which is G mod H plus, G mod K plus, and G mod L plus. And now in this case, these are two transfers. So the transfer and minus the transfer. And now if you really look at what this thing is, like when Fn is sitting inside this group, so this is a virtually free group. It's like a cohomological dimension, virtual cohomological dimension 1. And if this n is 1, then John Klein actually showed that this thing was, I mean, depending on n, this is either s to the minus 1, when n is 1, and when it's n greater or equal than 2, then it's a countable wedge of s minus 1s. So John Klein showed that, but what I'm telling you now is that it's not, and he showed this as like spheres with a trivial underlying homotopy type, didn't even look at the actions. And I'm telling you a homotopy type of that as a genuine thing somehow. So I don't know, like, how useful this can be in GGT. Of course, I'm investigating these questions, but certainly it's more information than just knowing that it's some wedge of spheres. I mean, it just like naturally shows up as a fiber of some transfer map. Okay, so that's one thing you can do with this thing. So now, another easy consequence of this construction is the following theorem, which we proved with Gijs. And I mean, comment again here is I had this paper of orators there as well. So potentially there is an alternative route to prove this theorem using this result of Garmelik, Knossen, Ramsey, and Janowski. So if suppose G has finite end of G, suppose G has finite end of G. Suppose G has finite end of G and E is Kane local with G action. Then the Kane localization of the Tate construction vanishes. So in some ways, or equivalently the map going from this kind of thing to this kind of thing is Kane local. I'll write here Kane local, the Kane local equivalence. So this is a form of this twisted ambidexterity of like in terms of like Bastian Knossen and some others that have looked at this. So if one funny advertisement I can say here is that recently I've been looking together with Gijs on application of this thing for homotopy cardinalities and things like that, because these guys apply these ambidexterity results. They define this cardinality of some kind of finite groups or K pi n's or something like that, and then they play around with these things and get some interesting results. So we've been trying to play around with the cardinalities that come out of these things, but that's a different story and I don't want to go into that. I think I wrote this in my abstract, but obviously I was way too optimistic that I will ever get there. I mean, definitely didn't manage that. Okay, so now in the last 3 minutes, maybe I can quickly say, well, first of all, maybe I can quickly give a proof of this. I mean, the thing is that you can, now the description of this dualizing complex allows you to actually describe this whole norm map in a very simple way. So you know this dualizing complex is that inverse limit as a genuine thing. So if you put here this inverse limit, so basically you put inside here inverse limit along this transverse of G mod H is HG, and then there is this norm map into E HG, right? So that's what it is. Now this is a finite limit. That's where finite end of RG helps. So you pull it out, because all these things are exact. So what you get here is an inverse limit along the transverse. I was asking around, where is this guy? But I'll give you a private summary of this, don't worry.
I started at 3.
Yeah, it starts at 2, but don't worry. Yeah. You've been prominently mentioned in this talk, you know. Yeah, so.
You were not here.
Exactly, you would get embarrassed, you know, of all this praise. So yeah, so this is what this diagram looks like. So this turns out to be inverse limit along the transfers of these things. This just ends up being inverse limit along the restriction. And of course here is the inverse limit along all the norms. So this is an easy exercise. And then of course we know that these guys are Kane local equivalents. So somehow the description of this thing as an inverse limit allowed us to actually describe this norm map as just an inverse limit of the norm maps in the finite case. Okay, so now let me clean the last board and write down keywords for other applications of this result, or actually what you do with the date. There is a date here, obviously, because like, well, it's K locally it vanishes, but what are the rationalizations, say, or other things? Right, so how many? I have lots of examples here, but probably I will never manage to write them down. Let me give you like keywords in the last minute. So one is, well, there is an HKR theory in this case, analog of HKR theory, analog of HKR for the rationalization of the state. So this I recently did with Wolfgang Luck and Stefan Schwed, where we actually studied the cohomology of BG for Morava E theory and base change to the character ring. We haven't really fully described the rational thing, but yeah. And another thing I also investigated, and in this case you can actually fully detect this stuff. So also if you do the date with periodic gate theory now, you know that this is rational. And in some cases, I actually computed the date cohomology, generalized date cohomology of PG for certain G's. For example, I recently computed the one for out f p plus 1. This was a funny calculation because if you compute this thing, let me just write this down and then stop my talk. So this is QP to the 4th when star is 0. Well, that's nothing funny, but this is QP to the 1 over 24, b minus 5, b minus 7, when star is 1, when p is greater or equal than 5, of course, otherwise this is not an integer, this thing. So, and why is this funny? I mean, like all this theory somehow allowed us to actually calculate this using some results of Luke on Chern characters. And this is joined with Naomi Andrew. So this is joined with Naomi Andrew, who actually visited here the last days, and we've been trying to finish this paper that actually calculates these things. So now, why is this funny? If you are computing rational cohomology of these out fn's, there is only one class in the world that has been constructed in odd-dimensional cohomology, and that's in H11 of out f7. And that was done with computers. And using this whole philosophy and all this date exact sequence and all that stuff, actually you can calculate this K1 of that thing and show it's non-trivial in odd degree without any computers. You can actually write it down. I mean, you need to do some geometric group theory for that, some centralizers and stuff. And I got some help, but you know, like this is sort of like how funny these date constructions can be and how interesting things they can actually carry around. That's an example. And I mean, if you start now computing some of these E-theories and date constructions on G for some kind of arithmetic groups, then you look at the calculations and number theoretic things show up, like class numbers and things like that, for obvious reasons, because you look at conjugacy classes of finite order elements in these things. So these dates are very interesting gadgets. That's what I want to say. Even if the K localization vanishes, what happens below is kind of fun to study. Okay, I think I'll stop here. Thank you.
Questions? Did I understand your last comment correctly, that you can indirectly now deduce the existence of odd-dimensional rational cohomology because the K?
I cannot, because the thing is, well, I can only say there is odd-dimensional thing in K theory, but I cannot say anything new about rational cohomology, and here is the reason why. I mean, the reason is that this K theory, this date K theory, or in general K theory without date of BG rationalized, splits with the Chern character. You know, in the Chern character, it splits as a rational cohomology, plus all the stuff with, you know, like here. Well, let me do p-adic, okay? All the conjugacy classes of P to the some power elements, so this like PD torsion things. The rational cohomologies of their centralizers. So in fact, in K theory, there is way more stuff, and here is QP coefficients because it got a bit completed because it's the Atiyah-Segal. Now, the K theory has more stuff than rational cohomology, and where we find these odd classes is on this side. And funnily enough, most of the centralizers are still even dimensional cohomologies because they are also some lower versions of these out fn's, basically. But in some funny degree, there is this one degree where one of the centralizers suddenly is acting on a tree, because it's like some kind of P and the N we are taking are close enough to each other so that this thing is still very simple before it goes crazy. And then we find that class in one of these guys, that odd-dimensional classes. And they're actually very few. I mean, like, it's not that many again. Like, it's only this degree we found it. We made a big table, and like all these K-theory groups are even again, except in that degree. And all the other odd-dimensional classes in K-theory come from here, wherever they exist. Okay? So now I do not know if out of this information I can deduce something about this, because this thing really lives in here. There is some Atiyah-Hirzebruch going on, of course, but then again, this is cohomology and rationalized outside-inside business, and that is funny with Atiyah-Hirzebruch spectral sequence anyways, so I can't quite tell you now I'm going to detect something in rational cohomology because you need two terms, something's going to survive or something like that, because you need to multiply the whole Atiyah-Hirzebruch tensor with a Q, and that's not gonna work, right? So you probably know that. So
So you just said P and N were close to each other.
yeah, P and N are
What
close.
is N? N equals 1?
In this case, n is p plus 1 out Fn, right? This is a special instance of out Fn where yeah, n is equal to p plus 1. And then the p are closed, then you can still capture some things. Yeah. And it's just by accident suddenly this odd-dimensional class shows up, which was a surprise to me actually when I was doing this. Yeah.
In your description of this dualizing module, do you get more of an understanding what it is? I mean, you could easily identify with the one-point compactification of the.
Yeah, so that's one thing I need to think about if it is some kind of Tom space type of thing. Yes, I mean, that is certainly suggested by this paper of Pardon, who does it for Sil showed me that paper. So this is this similar duality for Orbi spectra, which is some version of global spectra. And there he defined, I mean, it's very hard to read this paper, I was looking at it yesterday. But what he does is he does define some duality functor using some kind of, embeds into some kind of fancy representation, which is some vector bundle, in fact, or something, and then stacky thing. And then he does some tone construction in there, and that's this duality functor. And I believe there is a way of maybe also interpreting this in terms of that, or some kind of compactly supported cohomologies or something like that, which would then relate to some of these duality statements in geometric group theory. So in fact, this duality stuff in rational case just recovers the Bieri-Ekman duality for VCD finite groups, like rationally. So yes, in some ways there should be this kind of thing, but I haven't really yet had time to explore that. But I believe it is, yeah.
In the compact situations, the dualizing module here is invertible with respect to the smash product. So it represents an element in the Picard group, and you can think of things as being Picard graded. And the dual has the explicit description as the homotopy orbits of the dual of G.
Yeah, is that in the stable dualizing case? Yeah.
So being that's a presentation not of D, but it's Picard inverse.
Yeah.
As the homotopy orbit. So that sounds like a bit like a tone complex.
Yeah, yeah. I think
so it's plausible that it's the dual. I mean, the smash product inverse of this rather than itself. That is the.
It could be just like. Problem is that the smash product on compact objects does not even exist, because if you smash here two compacts, that's not compact anymore. So because of that, we tried with Kais actually to understand how does this DS behave with respect to smash product. And it is really true that the general dual is that's what I was saying, Grothendieck-Verdier duality, because it's d of x is maps from into this ds. So the only thing you really need to study is how this behaves. But then when you do tensor product with this thing, it's weird. We can't really control it in some way. So maybe, yeah, maybe we need to probably look again in your paper and maybe get some ideas. But yeah, we couldn't really say anything about what happens with smash product of this thing or in any kind of invertibility here or anything. Yeah.
Okay, I think we should say
Yeah.
it again.
Thanks.